Anil?
Thank you, Martin. It's quite cold in here. They told me that Singapore was a tropical country, so I'm going to try to warm us up by talking about something completely different now, which is reporting on about 10 years of work that we've done in an open source project called Docker. How many people here, just give me a show of hands, how many people here have used Docker in the past before? Okay, so most of you. So what I've been working on is a version of Docker that runs everywhere that makes it as easy to use as possible. So one of the key tenets of Docker that hopefully many of you will have seen was that our goal is to make the software process of building some software, distributing some software, and sharing it as easy and as friction-free as possible. So the basic idea is that I can just do Docker run of something, and then I can suddenly be in an environment where all of the software that the person who's publishing it intended to be shared is simply available. So in this case, I've got a playground for Oxidize OCaml, and then or OCaml 4.14 in that case, and I can just use it. And I can find lots of other images from around the internet. There's about 14 billion of these published, which represent the file system images of lots and lots of other people's work. So the idea is to make it as simple as possible to pull that off. And then there's something called Docker for Desktop. And what Docker for Desktop does is that it tries to take this experience and turn it into a native application. So the idea here, if you look at my little desktop here, is that there's a Docker little whale, cute little whale sitting in my menu bar, and it provides all of the installation and sign-ins and all of the stuff you need to do. But really, what it's trying to make happen is make that command line available for people to use. So given how quickly the Docker project grew, the idea was to hide as much of the complexity of managing all these bits and pieces behind a single native application as possible, and just drag and drop it and have it just work. And we released this software in 2016, and there's been hundreds of millions of downloads since then, lots and lots of daily users, and Stack Overflow has generally voted it to be a very kind of developer-friendly project for many years in a row. But there was some drama along the way, which is what I'll tell you about, and how we fixed it using functional programming. So a very quick timeline for you is where it all began. It really has felt like a very short period of time, but it's been a decade already. Docker launched as a bit of a side project at PyCon in 2013. And it just solved this problem that was a pressing one at the time of how difficult it was to share Ruby and Python code among each other. And then when I joined the project in around 2014, there was a real panic station happening because most of the world's developers use Mac and Windows, certainly at that time, and probably more so today. But all of the software was being deployed in the cloud using Linux. And so the problem became, how do you take a Linux application and run it as easily as possible on the desktop, which is what people are actually using? And so while there had been a rapid growth in Docker for the first year, there was a real kind of barrier being formed to make it usable. And so then this is where I came in along with a whole bunch of people who I'll show you at the end again. And we started hacking on some systems infrastructure to make it easier and more invisible to translate between macOS and Windows and Linux. And then we released a beta of this Docker for Desktop, and that's the one that really started the growth in adoption, as anyone with a desktop computer could just start using Docker and deploying it as well. And then some OCaml code came in that I'll tell you about that fixed some critical problems, and the growth continued. And then over the next 7 or 8 years, there's lots of really good developments and adaptations. So we released a lot of the components as open source. Apple and Microsoft integrated sufficient pieces into Windows and macOS to make all of this just work seamlessly. And then happily, a majority of professional software developers report they're using this as a result of this work. And then excitingly for ICFP, we've also started integrating a lot of shiny new functional programming features into the code base to keep up with the times for needs for performance and so on. And so we're using effect handlers and direct style IO, and I'll give you a bit of a preview about where we're going with that to show you what comes next as well. So this has been the overall timeline of where we came from. But first, let me explain to you what the basics of this application were and why we wanted to do it. The problem is that Linux containers are very Linux specific. There's a bunch of binaries that have been compiled, and they require a Linux kernel to run. You can't just swap a Mac kernel in there. And then our users are impatient. They simply want to run those binaries. And so we had to figure out, how do you build a native application that abstracted all of the gory details of running virtual machines, configuring the storage, making sure the networking works, and just make it so you just double click on this thing, and it spins it up. So our idea back then was, could we turn Linux itself into a function call? Can we just say, can we take the Linux kernel and do some stuff that will allow us to just treat it like any other library in our repertoire of libraries? So just like you link to libSSL, or you link to libmath, or anything else, could we do a liblinux? And then we built something called a library virtual machine monitor that made that possible. And so in the true functional programming style, our goal is to make Linux an implementation detail of the application. And the benefits are the users just have a simple application experience without all the gory details to worry about. Does that make sense? OK. Now, this would normally be really hard. Like Linux really does not want to be squeezed into a library structure. Linux is used to running in a complete environment where it runs all of the hardware. But luckily, another technology came along about 20 years ago called Zen. And Zen began this support for virtualization. And the idea behind virtualization is that you can fake out an environment where Linux can run, where it believes it's in control, but it's really running through software, device drivers, and equivalents. Now, the problem with Zen is that you can't run that on desktops, because Zen also needs to take over the entire computer, whereas we need to run as an application. But luckily, what happened was that in the intervening years since Zen, in about 2003, Apple and Intel and AMD and Microsoft added just enough support into the hardware and the kernels that we could have these little hooks to use hypervisor functionality from user space. But no one really knew that this existed. So we kind of did some rooting around and looked at some undocumented APIs and discovered that there was actually in green lots and lots of hooks available that if we used, instead of using them to run hypervisors, we could use them to run inside desktops. And then from there, the rest would be easy. We could build libraries to use them from user space. And then we could do the work in Linux, and we could run the whole thing as an application. So this is the 2016 plan. There's been lots and lots of different pieces, but it was all fragmented, and nothing really quite worked together. So here's how we kind of made it work, just to give you a sense of the architecture of this application. And then I'll talk about the functional programming pieces. So our goal is that we want to say run Docker run, just like I did here. I want to Docker run Debian. And I want it to run some command and have it actually do something useful. So the idea is that when I do a Docker run, it should download all of the images of Debian. And it normally does this inside Linux by running inside user space. There's something called a container runtime interface, which sets up the file system. And then it allows you to access the network. And then Linux does its job. It connects to what you want to find, and it returns what you requested. In this case, it's requesting the OCaml.org website. So this works great if you're in Linux. But then we want this to work when our client is on a Mac, yet it somehow has to find a Linux and go through and give us the result that we're looking for. So the way this works is we can build an application that links a hypervisor as a library to kind of pull this off. So we're just going to add a few more layers in between to see if we can just make this work without anyone noticing we've done all this stuff. So the first thing we do is whenever we launch our Docker for Mac application up here, we spin up this hypervisor framework. And the only thing this hypervisor framework does is that it hooks up the right hardware instructions so that you can actually run a virtual CPU or a set of virtual CPUs inside user space. So it takes care of creating the fake kind of virtual CPU environment. But it doesn't have anything else. It doesn't have an operating system or anything else. It just lets you run a function call. So that looks a little bit like this. It gives you some low-level C code where the interface that you have is that you can call into C function calls when they would otherwise become hardware operations. So if I need to spin up a virtual CPU or have an interrupt or the things that you would normally write low-level code for, they just become single-threaded callbacks into your application. So it's like a C function, right? And so in this case, we're just initializing a virtual CPU. And as you can see here, it's just creating lots of fake things for interrupt controllers and PICs and all of that kind of stuff. And then ultimately what it's doing is that it's just calling some functions. And we know how to deal with functions, right? They're just like any other library. And then from there on, you want to say, well, how do I want to program the rest of my operating system? So one path is write a lot of C code. And the other path is write it in a high-level language, because there's lots of policies that we want to deal with. So we want to figure out how to manage our storage and expose configurations to the application. We want to build a nice user experience. So the next thing we did was link in the OCaml runtime. So at this point, we have some low-level C code, and then we're trying to boot up a version of Linux. So we're like, OK, let's manage Linux from OCaml. And so at this point, just the standard OCaml FFI is linked into the application. And if you're familiar with the OCaml FFI, it allows us to just deal with low-level OCaml bindings, in this case for a block device, so we can have storage. And there's no real modifications. This is a standard OCaml FFI. But crucially, what this set of bindings does, it lets us shift our level of abstraction over into OCaml from the low-level code. And at this point, the first thing a Linux is going to need when it runs in your application is storage. And storage is notoriously difficult to handle, because you have file systems, you have to break things up, and users want to delete different things. They complain when they delete them, and then you have to recover them. So you need a lot of policy to manage it for this many users. So we wrote a custom file system in OCaml called QCOW, which is a storage format that is often used by virtual machines. But because of these bindings we did, we could take the low-level C calls from the low-level hypervisor and essentially build a file system that is much more expressive and high-level. So in this case, in the case of block requests, you're dealing with offsets to various parts of a sequential device with fixed size buffers. And our OCaml code that has been bound to the low-level HyperKit code looks like a request structure where, if you're familiar with OCaml syntax, we have an ADT here. We have nice high-level configurations. C structs represent blocks of memory. And then responses also look the same as well. And we have nice little error handling and so on, where we can pattern match and do all of those nice, good things. So at this point, we're now getting to our goal of running Linux. We have a low-level hook into our operating system. We've written bindings to manage the storage in OCaml, so we've got high-level code. We then do some gory details to manage shared memory, which gives us something to write into so that we can then communicate with Linux. And before you know it, we have an aperture where we've booted Linux successfully now inside the application. And in order to pull this off, you don't want to be booting up desktop Linux. So we wrote a custom Linux distribution that is fully immutable and boots up in just a few seconds. It's called Linux Kit, and it's still maintained. Last commit was 2 weeks ago. And imagine it's the minimum Linux you need to run Docker. So everything runs inside a container. It boots inside about half a second, and it does nothing. Its sole purpose for existence is to just set up everything you need to run the kernel. So there's lots of these kind of immutable Linuxes now, but Linux was kind of the first as well. And from there, life is good, right? In theory, you should be able to simply move forward and then bridge traffic to the outside world. And you do this by taking all the traffic that comes from Linux and just copying it and sending it over your host network, and everything should be fine, right? But then we got maybe, we released this, and we got maybe 10,000 bug reports in the first hour. There was a lot of users on GitHub, and my GitHub notifications haven't really recovered since. The problem was that every corporate user discovered that it looked like a bit like a virus, because from their perspective, it looks like there's a new computer that is transmitting traffic that isn't your desktop. And so we really had to figure out how to fake it out so that it looked like your Mac was sending the traffic, or your Windows was sending the traffic, not this weirdly hidden Linux library thing out there. And so the answer came from the 1990s. How many people here have used a Palm Pilot here? OK, there we go. Yeah, Simon's old enough in the back, but he didn't have one, I guess. But what these Palm Pilots did was, it was a way to manage your life in the 1990s, and you had to synchronize it with the computer. So it had a little protocol that would reconstruct the low-level network traffic from the Palm Pilot and turn it into high-level socket calls that you could then invoke from the other side, from an IRDA connection, an infrared connection back then. But the basic idea is that we want to take the low-level Ethernet frames and then convert it into high-level calls, and then use those high-level calls in order to replay the traffic in the Mac. So we've totally faked out exactly how this system looks to the outside world. We have no more hint of Linux at all. It just looks like the Mac is sending the traffic. The question is, how do we reconstruct this network traffic? You've got to start from low level. You need a full network stack, right? From low level Ethernet traffic. Then you've got to build up your views of TCP flows. then you've got to have HTTP flows, then TLS. There's a lot going on here. So luckily, in our repertoire of tools, we had something called Mirage OS, which was a full operating system written in OCaml for various reasons. It was fun. But what it did was we had all of the libraries in OCaml, and we'd already bound OCaml's runtime into our application. So what we did was we reversed the network stack by writing a bunch of code. And the reverse network stack looked at low-level traffic. It pattern matched on it. It constructed high-level data structures saying this is an HTTP request to this other endpoint. And then it translated that into macOS calls. And overnight, the bug reports dropped, celebrations were had, and the growth of Docker continued unabated. So what this Rube Goldberg's machine kind of looks like is that we've started off by spinning up a hypervisor. We've written some orange OCaml code for the storage. We then have a custom Linux distribution for the file system. And then we have a bunch of OCaml code to translate the outputs as well into something that the Mac can then use to look like it's just a native Mac app. So we've now successfully turned Linux into a function where everything from here to here is fairly high-level code. And then while there's a lot going on that's virtualized in Linux, it's no longer exposed. And there was quite a lot of OCaml code to make this happen. And I'm just going to spend a few minutes describing some of the good bits, the crazy bits, and the ugly bits, just to give you a sense of what our experiences were like using OCaml during this time. So the first thing is that because our networking code is so modular, because it's written in OCaml, we heavily used signatures and functions to kind of pull that off. So for example, here, we have OCaml signatures where we can include different combinators and signatures in order to assemble the structural interface we want for this, for example, for the output from the Mac or from Linux itself. And then we have maybe over 100 module types that represent small pieces of network stacks, and you can assemble them together. And then we can use OCaml's functors, which are parameterized modules, in order to choose which levels of implementations we want to assemble to match those structural signatures. So in this case, for example, we can bind into a socket, for example. We want to forward from the Mac, or we want to forward into the shared memory channels. And we could reuse a whole bunch of the signature implementations to make sure that we'd match the networking that was coming in to the networking that was going out. And then ultimately, the entire stack looks like a bunch of applications of functions. So I'll give you a very swift preview here where you can see OCaml code inside VPNKit, where we've got lots of higher order functors here making things. You've got lots and lots of applications of them in different formats. And then if I scroll all the way down, you've got lots and lots of pattern matches and stuff to intercept different parts of HTTP and kind of pull it off. But it's complicated, but it's a lot less crazy when you're doing it in high-level languages, because we can reason about things in a nice typeful way and use the OCaml module system to assemble the complexity into manageable chunks where we can test them independently as well. So generally speaking, the core OCaml features were remarkably useful here. So we often forget just how good it is to do ADTs and pattern matching and so on. And then just having a stable and predictable foreign function interface that hasn't really changed that much under our feet for over 10 years was actually really useful, because we were in one process. We were managing lots and lots of runtimes linked together in the same address space. So Swift, Go, OCaml, Objective-C, and I'm sure some other languages stuck in there as well. And it kind of made the whole thing a lot more attainable. But performance did start to drop a few years ago, and things were getting a little bit slower. And the problem is that we used a lot of monadic concurrency in user space in order to pull off all of the proxying. So this is classical OCaml, where we didn't really have any way of baking scheduling into OCaml. And so a lot of the code involved expressing that through some kind of higher level library. In our case, it's called LWT. More recently, we released OCaml 5, which has effect handlers. And that let us rewrite a whole bunch of complicated networking code to look much, much better. So just qualitatively here, the right-hand side is the direct style OCaml code, and the left-hand side is the code using LWT. You can see here on the right-hand side, we no longer have monadic binds. We simply use direct style copying. We no longer need to parameterize our inputs and outputs as functors. We no longer need to have error handling at the monadic level, because we just use normal OCaml exceptions. And the code has become just smaller, tighter, and simpler for that reason. So direct style EIO programming has been quite a successful use of taking something that did work before, but was very allocation heavy, and then turning that into something that is much quicker and more manageable. So that's the direction we're going in now. So overall, to summarize, OCaml's been a very solid choice for putting together a system that would otherwise have fallen apart under its own weight. Because there's just so many moving parts that it gives a clean abstraction boundary to manage the operating system side of an application while keeping it invisible from the user as well. Once put into production, it's been rock solid. There's been bug reports, but nothing that made us panic like those early days of 2016. So we've had hundreds of millions of users run this on all kinds of desktop machines as well. And this trick of using the kernel as a library is now emerging and is applicable to lots of other different systems. So WASL, for example, is WebAssembly running on Linux. I was just chatting to Ben yesterday about how we could pull this off. And so there's lots and lots of use cases for taking this architecture and applying it to other places where you might need to translate a Linux kernel into something that you want to manipulate from your programmatic user space. And of course, performance is good now, but it could be better. And so we ran a tutorial in Oxidized Camel where you've got Rust-style region management and so on. So that's another exciting direction where we're still trying to figure out the language aspects, but it looks like we should be able to get this to really good wire speed performance soon as well. So I'd just like to conclude by thanking many, many contributors to this project. We've had hundreds and hundreds of people contribute to VPN Kit. Some of them were named here. And generally speaking, my deep gratitude to the OCaml and MirageOS developer teams for helping us with lots of bug reports and assistance over the years as well. It's made the project possible, and we've really enjoyed working with them as well. Thank you very much. Whew. Oh.
And we have time for a few questions. Just line up.
Thank you.
The storage layer, was Ermin involved at all?
Ermin was involved. So Ermin is a Git-like management store for a while. We actually use Ermin for the coordination of the app through something called DataKit. So DataKit is now archived, but it's a Git-style coordination layer that would let you write things into a virtual file system, and then it would apps would use that as their logging layer. So it was never in the data path, but it was in the control flow path.
Thank you.
Thank you for the talk. I guess one thing I know about OCaml is that its Windows support has often been lacking, but here it seems to be that maybe even despite this, using OCaml helped the whole cross-platform thing actually be possible. I guess any comments on how that worked out, or if there are any things?
It's good. So OCaml's always had really good Windows support as a core compiler. So my colleague David Alsop works on this, and we had pretty much zero bug reports on the Windows side. Where OCaml is perhaps been lacking is the ecosystem of libraries, because that's harder. But in this case, we just build a monorepo. Everything compiles on Windows using the Dune build system, and there's almost no bugs. We have bindings to IOCP and things, which just take care of things.
That's great to hear. Thank you.
The story about enterprise software is a fun one. Reminds me of when TLS 1.3 came out and everyone freaked out and all the boxes were blocking the traffic. So have you seen security software mellowing out since and being more like chilled about seeing bridge networking interfaces all over their internal networks, or is it still a huge problem?
No, it's still a huge problem.
Still?
100% a huge problem. So there's more and more proxies inside networks now. So VPN Kit is expanded to support protocol level authentication. So you can authenticate to a corporate proxy with SOCs and so on in order to pull it off. So now it's more of a cooperative thing with the security proxies, but it still needs to reconstruct things in order to know what's going to be sent as well. So it's security is definitely not chilling out, but it's getting more manageable, I think.
Okay, good. Thank you.
Thanks, Joe.
Okay, and while we're just setting up, let me just ask a final question here. So, OCaml, where do you think it will have the biggest effect? Where do you see the biggest memory issues with the current
we do a lot of dynamic lifetime management at the moment. And so just having the ability to control regions and then make sure that we can do local stack allocation and do race-free parallelism. So all of VPN Kit is single-threaded right now. And so having a way to do structured multi-core parallelism and hardware offload would give us the next level of performance as well. So we'll get there. It might take a few years, but it'll happen.
Okay, let's thank Anil again.
Thank you.